Hey guys, we'll be talking about LOLs, low-level shells. Anyone has any idea why it's called LOL? You'll find out. So I'm Lise, this is Manish. So we work for SecureNet. I'm a penetration tester. Manish is a security consultant. And for this project, I am a independent researcher, but my company helped me bring this forward to you guys. So what's the story? Basically, the story is that I was trying to get a netcat shell, and my colleague at the time gave me like a switch. I was unaware that the switch was a layer 3 switch, and I'm like, well, you need an IP, right? Right? Well, that's only an assumption. The hypothesis is that layer 2 can be used for a netcat shell, but this would need to be post-compromise. So how exactly is that going to work? Well, we made this meme for you to kind of explain it. I'll give a couple seconds. So the thought process. We'll need a MAC address, and all layer 3 traffic is encapsulated in frames, which means that you will need an IP. But what tools already exist that kind of accommodate this? And there's a tool by the name of ARP Exfiltrator that was made by Antonio Blesia. And he was able to exfiltrate ARP requests back and forth between two nodes. And he suspected that this could be used in a C2 framework. So, in other words, it's possible, but with ARP. So when life gives you layer 2, make a layer 2 shell. Bottom line, it's possible to encode information in frames, but not through encapsulation. So why is this such a big deal? Well, the big deal is that layer 3 and above is highly monitored, layer 2 is not, which means that communications don't actually need IP or port to work. So how does layer 2 work? Well, we have 802.3, 802.11, which is wireless, and it work on the same frames, same headers, and all our payloads, all our stuff is going to be stored in the payload header of the frame. ARP broadcasts to all nodes on the network using the FFFF address. But other protocols can do the exact same thing. There's no difference. The ether type is what defines a protocol, and in IANA, you can register your own ether type, which we'll get into the next section. Ether types, why are they so important? During DEF CON 31, Richard Lachey, he did a talk about this in his talk, Fantastic World of Ether Types and Where to Find Them. His talk was more about how to use ether types and how to structure them to communicate with devices. In our prototype, we will not be using ether types specifically. We'll be using them to blend them in, to make it more covert. So here's the payload. We have 1,500 bytes that we can work with.
So broadcast domain communication. So as we all know, whenever we get a broadcast message sent on a layer 2, it gets sent out to all the devices that are connected to that switch. So why is this important? We were trying to see if we could include netcat, PowerShell, SSH commands in these broadcast domain messages, which could be sent out to the other systems that are on the broadcast domain. So let's see what are the requirements and what the data flow looks like for doing this. So the requirement, as Elise spoke, this is a post-compromise tool, so we are going to need initial compromise. In addition to that, we need Python and C# to be available on the compromised system. Binary, if you're using anything, for example, netcat, if you're using that, we will need that, and a loader of some sort. So this is, in a nutshell, what is happening. The victim is sending commands via Ethernet frames, and the victim is responding with Ethernet frames back with the response. So let's take a detailed look at the flow. So yeah, the attacker starts off by sending Ethernet frames containing the command. The victim node then decodes the frames, extracts the command, and executes it. Once the command is executed, the victim node then again uses Ethernet frames to send the information back to the attacker node. So let's take a look at a demo quickly for this. Before I jump into the demo, I want to show the commands that we are running. On the victim node, we are running the script in listen mode and setting the attacker and session ID. And on the attacker system, we are running it in connect mode, again, setting the same attacker and session ID. Additionally, we are providing the MAC address of the victim machine. And then we'll be running whoami and dir command. As Elise spoke earlier about ether types, for the second section of it, we'll be using STP as the Ethernet type. The code for that is 8181. So let me pull the video. So yeah, on the right-hand side, we have the victim screen using Windows, which is connected in listen mode, and then we are using the Debian machine on the left, on the right, to connect to the victim. We are running whoami and dir command, and we have Wireshark running in the background to capture the packets. So as we can see, the commands that were sent were using loopback, and the responses that were received were using broadcast messages. So now we'll take a look at the ether type that we spoke about. So the only difference between the two commands is we are specifying the ether type this time round to see what sort of communication it happens. So the ether type, we are using it to blend in. So again, we'll run the same commands, whoami and dir. Yeah. So let's take a look at the Wireshark capture. We'll do the filter for 8181. So as you can see, the commands were sent using STP this time around. So yeah. Okay. So is broadcast communication required? Absolutely not. We could use point-to-point communication as well. The reason why we chose broadcast for this particular example, because broadcast communication is usually noisier and it gets some time lost, and like sometimes the security tools ignore those.
So to kind of prove the point that communication not only can, like, we can tunnel layer 3 and above, we're going to be tunneling netcat in the next demo, which the prototype does support. This is the kind of diagram of what's happening. I'm not going to go through it, but basically we do the exact same thing. The attacker sends the Ethernet frame, the victim receives it, it then decodes it, it sends it to its own loopback address where netcat is listening. Netcat can then run that command. The response is sent to its own loopback address and then out to the out through Ethernet. The exact same opposite happens when the victim is listening, and this enables two-way communication back and forth. But this not only works on netcat, this works on anything. So here we have the attacker panel. The thing that's highlighted, that's where you type in commands for netcat. I'll give everyone a couple seconds. The victim panel here, what's highlighted is the actual netcat command. On the right side of the screen, that's the tool that's being for L2 shell. Okay, we're going to make EDR cry now. Okay, so on the right side, or sorry, left side, that's where the L2 shell is. We're opening up a RDP port, or an RDP session to the victim machine. Now, the reason why we're doing this now is to show that we have the initial compromise. And, okay, that... Sorry about this, we're having some technical issues. Okay, so we have a EDR solution that's on the victim machine, and the threat detected, that's only netcat, that's not L2 shell. Once an administrator manually locks this up, it will actually cut the RDP session. Basically, nothing will be able to communicate to that device on any known protocol. So that's what happened here. However, we have here the L2 shell that was initialized earlier. We can still communicate to it via Ethernet. Okay. I'll just close that. This is essentially what happened. Frames, they do not get get detected, and they are EDR, IDS, they allow it to pass through. This is all the loopback traffic that happens on the host and the victim. It never appears out of the network. So what are the limitations of this? Well, obviously we got the broadcast domain, and the frame headers, they're cut off by the routers once they traverse to different networks, but we can bypass this with a NIC. We can do VLAN hopping, directed broadcasts from routers, layer 3, 4 application layer protocols, out-of-band bridges. These are all ways we can extend from one LAN to another. MPLS networks, this works on MPLS the same way that it works on any other ether type. MPLS circuits can enable that communication. Internal ICS networks are very flat. It allows it would be a prime target for this.
So we could also do layer 2 forwarding. So if there is a victim machine that is compromised, we could jump from one NIC to the other one, basically hopping the subnet. We could also create temporary layer 3, layer 4 bridges with this, basically accessing restricted subnets that could have like DLP preventions on them. So the use case that we can think of is a red teaming scenario where, or like a C2 extension, basically where we are using this for communication between the compromised host. So out of the 6 hosts that are here, we are using, 3 of them are not using the L2 shell. So they are at risk of getting compromised. However, the ones that are using L2 shell, they would be very hard to detect.
So now this is kind of the grim part of the presentation, detections. Unfortunately, we will need layer 2 sensors. We'll need to span tap the traffic. This might work on 802.11. It works on 802.3, so just regular Ethernet. The entropy and size of packets, they're going to have to be looked at. The expected ether types, for example, if you have the configuration test protocol on your network, it probably should not be there in the first place. The only way to really know this is to baseline things. Signatures, good luck, have fun. It might work. However, this is only to detect common commands that they're unencrypted. Zeek might, out of the box, Zeek is not going to detect it, and it's kind of expensive to utilize. Another detection is to inspect the loopback traffic if our technique is used. It's an adjacent issue, but it's good when paired with covert communication. It's not just a network or endpoint problem anymore. So take a picture of this. This is going to be how you detect anomalous traffic via Ethernet. Now, if the traffic is not anomalous, it's a lot harder to detect. So here's the good, the bad, and the ugly for detections. If it's IPv4, ARP, or IPv6 ether type, it's significantly harder to detect. So the highlighted green, that's all the detections with anomalies. The above is basically IPv6. You can't really tell the difference. So defenses, VLANs, that kind of depends if you're only working on one NIC. Isolated guest networks, I couldn't break through that one, so it might be good. There's certain limitations to it. And cloud environments, it depends how layer 2 traffic is implemented on them. What has been in the wild? There has been a APT group, Platinum, that utilized SOL in their C2 framework. However, when I looked closer into it, it seemed to use IP. IP is not used in this prototype, so it's similar but not quite the same. So closing remarks, this is not a vulnerability. This is basically frames without structure are still frames. Layer 2 detections only work for known attacks. DPI, unless otherwise configured, isn't really looking for this. Wireless devices can communicate on Ethernet to other Ethernet devices. Works in line. So it's system network agnostic as long as 802.3, 802.11 are supported. And has this research been performed? I referenced all the people that have done similar research. I haven't really found anything quite to this extent. However, there is a references page that will show everyone who did similar. TLDR, it's command control focus, Ethernet transport agnostic. There's ether type smuggling. This evades most layer 3 to 7 IDS without disrupting other network hosts. And how does everyone feel about supply chains? Because that could be problematic if this is used as a technique. Million frame question, are adversaries using this? I don't know. But now that the EtherCat's out of the bag, what's next? Should vendors do more, or is this a free-for-all? So here are the references. And big thank you to BSides Las Vegas and the security community. Special thank you to Steve Porter, Doug Leese, and Quinn Kramer for helping me and the team make this happen.
Questions?
Any questions? Sorry. Sorry, which slide? Can you come up to the microphone, please? Sorry.
Yeah, the command to detect the traffic, the TCP dump.
Oh, I see. Okay. Yeah, this is it. This is only going to detect anomalous traffic. This won't detect frames that are properly structured and basically that are made by not amateurs. I don't know.
So I'm understanding this correct. Like you said, this has to be on the broadcast domain. The two device, your victim and your aggressor have to be on the same broadcast domain, right?
Not necessarily. It depends. They can be on different networks, but the actual communication, it happens on LAN. But if for example, there's like multi-NIC, so you can jump from one network to the other.
Okay. This wouldn't work like if it had to go through a switch, because it would, like you said, it would strip the hold it. Well, I guess what I'm getting at is the value in this is it would require your aggressor. You would have to have some sort of, if you wanted to use this as a remote attack, you would have to have some sort of channel to get to it.
So this is post-compromise. So the consideration here is you already have compromised the victim machine. You are already on the same network as them. So it could be something that you use for pivoting, for covert communication. So it's basically sort of, you could think of it as a C2 extension, basically. So,
Okay, but both of them would need to be compromised, the victim and the aggressor.
So initially, once you have compromised, you would be on the same network, right? So
Okay,
from
but then
there, you could move on to a different target who is in a different network.
And then you still have to be able to bypass the EDR to,
Yes, if that is the case. But the thing is, layer 2 isn't monitored that
no,
much.
layer
So,
2 isn't, but in order to get the initial compromise.
Yes.
Okay.
Yes. So that's the only consideration here, initial compromise. So yeah, this is after this is post-compromise, and it's mostly for covert communication.
So actually, now that I'm thinking about this a little bit, where this might be of value is like if you're doing a pen test engagement where you actually get physical access to the facility and you somehow put a malicious device
Yeah.
that connects directly to the network, but
Yes,
then you have remote
yes.
access via some other.
Yes.
Okay.
Yeah.
Okay,
Yeah.
cool. No, not that discount what you guys done. This is really cool.
Thank you.
Hello, just checking my understanding. Do you need raw sockets for this to work or not?
I'm sorry?
Do you need raw sockets to do this or not?
You need admin privileges, so this requires sudo, but it does, like raw sockets, it would work on IP, right? But this would be pure frames. So in a way, yes.
Okay. Have you considered doing this same type of payload but using setting the protocol to be IP, but just have invalid payload inside the IP packet?
I didn't quite understand that. Sorry.
If you're making raw frames, have you considered having something that is labeled as being an IP packet, but just with random content?
So we are not really using IP. So it's either broadcast or Mac to Mac.
Okay. Yeah.
Hey, are you going to be open sourcing any of the code you showed off today?
We're considering releasing this. We don't really know the impact of this right now, but we're considering it. Raise a hands. Who would like this release so they can look at this? We need a lot more hands than that.
All right, thank you.
All right. Thank you. Come on, wrap up.